So we wanted to establish the bijection between the two sets, right? Uh, right. So we wanted to establish this thing by torsors. So last time we talked about what's the torsor, and so the plan is to first establish the bijection between the torsors to this group, like H1C mu, where mu will be any sheaf of abelian groups, but for our purpose, we will be interested into this sheaf. But today I will talk about in general any sheaf of abelian groups, and C will be any side. So for today, uh, so let's first define a few notations and then start. Uh, let's get started. So so mu will be my start from here. So mu will denote always a sheaf of abelian groups, and we first define this category. So this is from the name itself, it's obvious that any object in this category is a short exact sequence of sheaf of abelian groups of this form. So Z is the constant sheaf on a site C, and mu is the one that I fixed at the beginning, and epsilon will be another sheaf of abelian groups on C. And morphism, when you talk about, then it will be, let's take another element, let's call it epsilon prime, let's pi prime. Yes, so morphism will be a morphism of sheaves such that these two small squares combine. So there are two things to note. Firstly, that any morphism is an isomorphism. You can argue via five lemma or something. Secondly, given any object in this category, given any object in this category, its automorphism group can be identified with with the global section of mu. And we will actually need both of these facts later. These two are you can, or you can prove them both. Of first one is obvious. Second one is also not that. So so now what we wanted to do is, so we wanted to define a functor from this category to the category of mu torsors. So remember, torsor is a sheaf of set on which mu acts simply transitive, and sections must exist locally. And if there is a global section, then we call the torsor to be trivial. In which case, it will be actually isomorphic to the sheaf of abelian groups, mu itself, and the map will be just via left multiplication. So we define a map from these two. Uh, this category. So let's take a short exact sequence, which is a typical element. And let's send it to, we will denote it by CP, which is, so we have the global section, right? So one is here. So you take a pullback of them. And you can firstly check that. This is easy, I'm not doing. Check. The P is indeed a mu torsor. So that means sections exist locally, which of course does by the property that this is actually a, oh, This is a short exact sequence of sheaves. So that means the last map is locally surjective. It may not be globally, but it's at least a local surjection. So sections exist locally because you have pullbacks of the element 1. And secondly, the action is simply transitive, which is almost obvious, again from the short exact sequence. So it is indeed a mu torsor. And the claim is, let's write it as a theorem maybe, that this functor, the functor as above, is an equivalence of category. So we'll first prove this. So proof. So so basically, to show it's an equivalence of category, we need two things. One is it's a fully faithful, and secondly, essentially subjective. So let's start with essentially subjective part. So so let's start with, let's take a torso and a covering of the final object, covering of the final object in C. Because mostly we'll be talking about schemes over a fixed scheme, there is always a final object, so you can stick to that assumption that there is a final object in a set. And by the way, so one thing you may wonder that why there is covering by a single object. There could be some bunch of objects with bunch of maps, right? Xi with some maps too. But the fact is, if your category is nice enough, then it's actually good enough to consider one map. Because so so let me write in this way. So that's separate fact. So if coproducts exist in C and the formation of coproduct commutes with fiber products, if they exist, then so there's a natural functor way. Then for any set of objects, then for any set of objects, the natural functor, so it's there's a natural functor for me by definition of product and people is an equivalence of category. And eventually, in order to prove this theorem, we'll use the property of descent. So basically, it's good enough to consider map from exactly one object, because then if you have a bunch of objects, so if uh, you have say xi be a covering, then you may just take the disjoint union of xi, let's call it to be q, then it's actually same thing as, so for p, we have that category of decent data. This is equivalence if and only f of e to f of uh, That is it. So actually, it's good enough to consider uh, covering by one. So that's why we are taking one now. And so now, so basically, we want to construct an element in that category X. Okay. So again, without loss of generality, that is the end of the code. So without loss of generality, assume that P of X is non-empty. Because otherwise, you can go to a further cover uh, over which there is exception. Let X section, and you have then the two projection maps, right? That is the first component, and you have the projection on the second component. And now you can consider the pullback via both of these projections. And since it's a torsor, if one particularly acts simply transitively, there exists a unique element alpha over x prime, where for me x prime is x cross x over e. These are all over. The x is over. Such that uh, alpha with this is, so these are the standard notations of pullback via these maps. And further, let's denote x double prime to be the triple. Okay. And there I claim that so this will be my notations for the various projections. It will be Q12, Q23, and Q13. So that means for Q12 means it is projecting on the first and second factor. When we consider that as x prime, and similarly for the Q23 and Q. So the claim is this plus, and it's how do you show? It's simple. You just first you take Q23, Q2 star x, which is P alpha times P1 star x. Now you apply alpha, and you use the isomorphisms. Yes, so that is as it is. Again, we write it as uh, oh, no, should be alpha, should be x, not alpha. And then P2 star x is again alpha times P1 star x, which is just star. Remember, we are taking mu to be sheaf of abelian group, so my operation is addition. And on the other hand, you can compute it uh, in a different way. So that is one way. On the other hand, you can compute it in this way, where it is same as um, Q13 star, Q2 star, which is alpha P1 star x, that is Q13 star alpha, and then finally we have Q 1 3 star, 2 1 star. Okay. So what we get is, and these two are again same, or I mean isomorphic. And how do you remember which two of them are isomorphic? So the way I think is, so P1 star means basically you consider X as X tensor 1. That's how we can imagine. And P2 star means, that is P1 star. P2 star means it is 1 tensor. That's how we can remember. And then when you further go to Q13 star, let's say, so that it means over the second component, you are already putting 1, and over the first and third component, you are distributing the first factor x and the second factor, which is again 1. Okay? So let's verify one of those things just briefly. So I wrote isomorphism between these two. So that's now from there it's obvious because this is, so first you are pulling back by P1, so that you can imagine as extensor 1, and then you are pulling it by Q13 star. So that means over the second component you are not doing anything, and you write it with the first and third component. Now what about this? Again you are pulling back by P1, so that is this. Now over the third factor you are not doing anything, and so you see both are same. That's how you can think. And similarly, if you apply this process, all the other isomorphisms will follow. And okay, and again, because the action is simply transitive, these two objects must be same. So you get uh, what you want as it is. Now, why it's important? False. So now, so we have the element alpha to begin with, which was in new x cross x, which we are denoting by x prime. So we can associate to the torso an extension as follows. So, going to define such an extension, and what we will actually do is we will define the extension over. So, the trick is to define the extension over x. We define the extension over this category, over category over x. So, objects are all the objects in C that are over x, and morphisms are all the morphisms between those two objects such that the obvious triangle computes. So to define the extension over C over X with respect to the covering, respect to the descent data. And now it's there is an obvious choice to take what's an extension because uh, what we will do is basically we'll just take the trivial extension. So take the trivial extension. Take the trivial extension that is just the direction. And it's actually easy to guess why we are taking it because so we assume the section exists over x, right? So we assume that this is, so that means when you restrict the torsor to c over x, basically it's just because there's a global section, right? Because x is the terminal object, so that means this torsor is trivial if you restrict it on just x. So that means the corresponding extension will also have to be trivial if you already assume that the fact is true. So that's how we are just tracking it. So, so take this extension, trivial one, and uh, and we need an isomorphism, right? So for the isomorphism, let's call it sigma over the fiber product. So remember that is this. We take the map, so this. So what we do? Let's take any zeta and in we send it to this. And now you use this fact, which we have proved, to actually show that uh, let's call it star. So use star to show that sigma satisfies the co-cycle condition. Right? And then you will get an extension. So how do you get? So remember, we have the this fact for category of sheets. Let's write it like this. Hmm. So again, it's a separate fact theorem that any covering in C is an effective design. Morphism in sheets. So what do I mean by effective descent morphism? We have an obvious functor. That is an equivalence of that. So just to recall what is this thing. So any object, so any object in this category, how does it look like? It's simple. You take so any object is okay, so any object will be a pair. um, say E sigma, where E is fiber over X and sigma is an isomorphism over the two pull web by the two projection. So again, projection 1 and 2 is just same thing over the first factor over this such that over the triple intersection there is this obvious co-cycle condition. Sorry, that sigma satisfies co-cycle. And then you can obviously get a map from Fy to this category because if you already start with an element over Y, so an object, let's call it Xi, so that is over Y. So via pullback, you will get an object over X. So that will define you a map. That will define you an object in this right hand category. And for sheet, this is an equivalence of category. So what we all in all did, so let's just recall. So all in all, we just defined an object here. Okay? That is what we did. So in this case, we have a map from X to the terminal object E. We defined, uh, let's say, we defined an extension which is basically trivial over X, and we also defined the sigma, which is basically projection, the pullback of that object via the projection, which was an isomorphism. And right. So now using this fact, this is an equivalence of category, you will get an object here, which is basically an extension, the one we require. So that extension, I will call it by script E, script P, the one that I started with, this one. So that is that object, which we used from this fact. That this is an equivalence of category. Okay. So that's how we can show that it's the functor is essentially surgical. And now the last thing we have to show that it is fully fetched. That means build the map between home is a luggage. That's easy. So let's take two extension and the corresponding torso. Now remember, any morphism is an isomorphism in extension. So basically, and also remember the fact that uh, the automorphism of an object can be identified with the global section of mu. So now from that, it's obvious that this map is 1-1. Because if you take two homomorphisms, basically isomorphism, between extensions, say f and g, such that they map to the same homomorphism between the torsors. So you can consider fg inverse, that will be an automorphism of that object in the left hand side, which will go to basically identity in the right hand side. So, so then that automorphism, if G inverse, will be can be identified the global section of mu, meaning that F and G are so F and G they differ by an an object and so let's say so let's do that. So F and G, let's take that. Let's say mm, so basically what is it? So this is locally the pullback of this. So this pi. So so let's say if and G, they both goes to the same thing, whatever it is. So 5 years. So then you can consider if G inverse, there will be an automorphism of an object in the left hand side. So that you can identify with a global section of mu, meaning F and G differ by global section of mu. But that is basically what is the map? That is a sub. You can think of it as a subsheaf of the epsilon maps. This pi 1 inverse and pi 2 inverse of 1. So there is a restriction of these two maps, F and G. So over the restriction, they are same, and throughout they differ by an element in the global section. So if you then it follows that the element that is by which the two morphisms are differing has to be one, right? Because when you restrict the element, the global section of mu becomes one, but it's a global object. So throughout it has to be one. So it's injected. That is tautology. Now you need to just show the subjectivity. So start with a so if sigma is an isomorphism of torsor, an isomorphism of torsors, then so you know that morphisms of sheaves you can construct locally. So it's enough to show that such an isomorphism between the two extensions exists locally. And now you can consider you can pass through a say a covering of the final object E, and then it reduces to show that so it basically it's enough to show the case when both the torsors are trivial, right? Because over locally sections exist, so locally torsors are always trivial, and there the result is obvious. So then we may pass through locally. i.e., it's enough to consider mm, the case where P1 and P2 are trivial Torsors. And so in this case, the result is in. So all in all, what we did is basically we showed that this functor uh, is so what is this? Right. So this functor is an equivalence of factor. And lastly, so what we wanted to actually do, we wanted to show bijection between these two. We have actually got to halfway stage. That is till here. Now we want to link these two, and that is easy. So what one does is the following. So in this case it should be given, but here we are doing for general sheaf of. Okay. So what we do? So now we want to establish from this to each one C. C is the set. So let's again start with an object here, and so this will induce exact sequence. Right? So it will be C new plus each one C new. You have so that is so you have the element one here. Let's call the connecting map delta. We take del of one. That will be the object that will be assigned to. And you can actually show that this actually defines a bijection between these two sets. So phi is a bijection. And how do you actually do it? So I think you start with uh, an element in each one. So firstly, you embed the sheaf into an injective sheaf. So that means what? So embed new inside an injective sheaf, and you define the co-coordinate to be script q. I think it should follow from. So we have this. Now if we apply cohomology, what you will get is um, so you get gamma. So I'm writing this way. So then h1 c mu. Then you have um, h1 c script I, but then script I is injective, so that is 0. Okay. You have an object here because you want to define a map in the other direction, right? Which is that means you want to come up with a short exact sequence of sheaves like this. So you need to fill that void. And I think so. You have an object here, say zeta or whatever. You can take the pullback of zeta because this map is surging because there is a zero. And I think mm, okay, so you can take a pullback of that, which will live here. So I think then you can take this to be Q. I'm not sure, but I think it should be. Then that will basically give you mm, the bijection, if I'm not wrong. So, but yeah, so the map in one direction is for sure. This is the map. I just have to verify if this is indeed the what do you call the inverse of that. Okay, so and that's how you basically get this thing. Okay. And so, in the first part, what we did, we defined bijection or an equivalence of category. In the second part, we did the solenoid here and bijection here. And now we'll specify to the case where this is mu in. So let's recall these are all invert. So these are all invertible regular function whose nth power is 1. And so from that we'll try to fill the left hand side, and the scheme will be spectrum of a field. That's just a point. The left hand side will eventually become this, and the right hand side we want to identify with this. So, so yeah, that will be the content for the next. So yeah.